Hello there guys, how's it going? Mike coming back at you here with another video on vector calculus. In the previous video, we talked about the wedge product of differential forms. We went through the properties and the basic operations that we do with it, and then we saw a couple sample problems where we calculated the wedge product of some differential forms. In this video, we're just going to go through a couple more sample problems here, get us all some more practice, get comfortable with this operation being the wedge product. I'll let you guys try these problems on your own, and then we'll go through them after you think you found the answer. Now, when we're using the wedge product, we're only going to be using the wedge product for multiplying or taking the wedge product of two one forms or a one form and a two form. If you think back to the first video that we did on differential forms, taking the product or the wedge product of any differential form whatsoever and a zero form is really straightforward, almost trivial. And we said from our previous video where we introduced the wedge product that we only take the wedge product of K and L forms when K plus L is less than or equal to 3. So that only leaves us these two cases of taking the wedge product of two one forms or a one form and a two form. But here's our first example. Let's get right into it. Alpha and beta are both one forms. You see them given right here. And we want to find alpha wedge beta. We want to find the wedge product of these two guys. So take some time, refer back to the old video if you have to on those properties of the wedge product and work on this guy. Try to figure out what the wedge product of alpha and beta is going to be. Once you think you have figured it out, press play on the video and we will see if your answer was right. So pause it here for now and then we'll be back with you shortly. Okay, so let's see what we get when we take the wedge product of alpha and beta. So alpha times beta, just making the simple, straightforward substitutions of these guys. And now what we're going to do is we're going to use the distributive property from our previous video, and we're going to multiply these things out. Really, all we're doing here is we are just foiling these things. So make sure every term gets multiplied with every term. So the e to the yz dy is being multiplied into each term, and then the cosine of x plus 3 is getting multiplied into each term as well. Now, as we said in the previous video and as we saw with our previous sample problems, the zero forms, the functions, the x's, y's, and z's to powers, the cosines, the sines, all that stuff, those guys you can multiply with each other and move those things without any trouble. But you have to maintain the order of the dx's, the dy's, and the dz's. You have to maintain the order that they are showing up in when you take the product of these things. And when we FOIL these things out, we come down to the next line right here. 3x squared yz squared e to the yz times the dx dy plus e to the yz sine of x squared dy times dy, and so on and so forth. Just very straightforward multiplication of the individual one forms making up these two one forms as a whole. Now we're going to see that some of these terms can be canceled out, and some things we need to switch the order of some of our basic one forms here. We know that if we take the wedge product of any one of our basic one forms with itself, then you just get 0. And we know that if we take the product of anything with 0, we get 0. So we have a dy over dy showing up here. That means this whole term is going to go out to 0. And we have a dz times dz there. So this whole term there is going to go to 0 as well. So we're left with 4 terms, They each have a different basic one form. We have dx wedge product dy, dz wedge dy, dx wedge dz, and dy wedge dz. Now, our basic two forms show up in cyclic pairs, dx dy, dy dz, or dz dx. And we have to make sure that we put these basic two forms in these cyclic pairs. So for a couple of these terms, we do need to make some switches. We do need to switch the order of our basic one forms so we get that proper cyclic pair. And when you switch the order of two one forms, you're going to multiply by a -1. So we have the dz dy here. That needs to turn into a dy dz, and that's going to change this sign there to a plus. And then here we have a dz dx, and that needs to change as well. And when we make that switch, this is going to turn into a minus sign here. And when you do that, you come down to this next line right here. We also remove the wedge in the middle of our basic one forms, because from our previous video, saying dx dy or dy dz or dz dx is just saying dx wedge dy, dy wedge dz, and so on and so forth. So we're almost there. We just want to recombine some terms so we can make this just look a little bit nicer. I have this batch of stuff here times a dy dz, and then I have this batch of stuff there times a dy dz as well. So we're just going to recombine those into one term, and when you do that, you come up with your final answer. 3x squared yz squared e to the yz dx dy plus the quantity e to the yz times arctan z plus sine of x squared times cosine of x plus 3, that whole thing times dy dz, minus 3x squared yz squared cosine of x plus 3 dz dx. So this is our example of taking the wedge product of two differential one forms and coming up with a differential two form. Recall that if you take the wedge product of a K form and an L form, then the resulting wedge product is going to be a K plus L form. So let's move on to our second sample here. In this problem, we have alpha and gamma now. Alpha is xy dy dx plus yz cubed dy dz, and gamma is z times the secant of x dx minus x to the fourth times y dz. And we want to find the wedge product of alpha and gamma here. So you see that alpha now is a 2 form, gamma is a 1 form. So we know that the final answer, the final result should be a differential 3 form, because 2 plus 1 is equal to 3. So that's a little sort of check you can use to make sure that the answer you came up with is indeed in the realm of possibility of being a correct answer. So once again, pause the video here, take some time, try to figure out what this guy is going to be on your own. Once you think you have it, press play and we will go through it together and we'll see what we get. All right, so let's see what alpha times gamma is. Once again, we're just making the simple, straightforward substitution. And once again, we are going to kick it off by using the distributive property, aka foiling this thing out. So this guy being multiplied into each of those, and this guy being multiplied into each of those guys there. When you do that, you come up with the following. xyz times secant x dx dy wedge dx plus yz to the fourth secant x times dy dz wedge dx minus x to the fifth y squared times dx dy wedge dz minus x to the fourth y squared z cubed dy dz wedge dz. Now we need to do some simplification of these two forms slash one forms here. How do we deal with these guys here? Well, if you think back to the previous video, I mentioned a quick little shortcut as to how you can sort of nicely take care of some terms when you're taking the wedge product of a basic 2 form and a basic 1 form. We said that if you get the same basic 1 form showing up in both terms in your wedge product, then that whole thing is just going to go to 0 because you're going to be taking the wedge product of a basic 1 form with itself. So if you're seeing two dx's and you're taking the wedge product of dx and something with a dx in it, that wedge product is just going to be 0. If you take the wedge product of a dy and something with a dy in it, then that term is just going to be 0. And similar with dz and something containing a dz. So in this first one here, we see we have a dx as part of my dx dy, and we're taking the wedge product of that and dx. The same thing is showing up in there. So this whole term is going to just be wiped out to 0 because the wedge product of our basic 2 form and our basic 1 form is going to be 0. If we look at our second term, there are no basic 1 forms in common here. So this guy is going to give us something, and because there's only one basic 3 form that we have, we're going to see that this is a 3 form here. Now the question is, do we have to do some switching of these 1 forms to get it into the proper cyclic order? We're going to see whether or not we have to do that very shortly. In the third term here, we have a dx, dy, dz. Again, there are no basic 1 forms that are repeating themselves, so this is going to give us a 3 form. Once again, whether or not we have to switch the order of some of these basic 1 forms is yet to be seen. And then looking at our last term here, we have a dy, dz, wedge, dz. The dz is showing up in each term, so that means this whole last term here is just going to be 0 because that wedge product is going to be 0 here. So when you do that, those two terms, the first and last term, cancel out, and this is what we're left with after we just remove the wedge in the second and third terms. Now the question is, did we have to switch the order of some things here? Well, the basic 3 form in cyclic order, in proper cyclic order, is dx, dy, dz, or dy, dz, dx, or dz, dx, dy. And we have both of those things happening here. We have the dy, dz, dx, and we have the dx, dy, dz. So these basic 3 forms are in proper cyclic order. I can just restate this guy here as dx, dy, dz, and it's going to be the same thing. And then we just pull the basic 3 form out of each of these terms here, and we come to our final answer. yz to the 4th secant x minus x to the 5th times y squared, all that times dx, dy, dz. So we see that we're getting what we should be getting. We are getting a differential 3 form, and from what we know, this is what we should get. And we went through each step of our process, and we logically arrived at the answer that we got to.